you sure you don't want one thing like that?
No, blue jet. Jet blue.
Is that, it's
That means
Say again? Okay, thank you. All right, welcome everybody. Thank you for coming to today's seminar. It's a pleasure to have here Dr. Guillermo Sapiro from Duke University. He's actually somewhat new to the area. He's been for many years at Minnesota. Dr. Sapiro is very well known in computer vision in general and applied mathematics in particular in this case. He did his MS and PhD from at the Technion in the electrical engineering department in Israel, and finished in '93. After that, he came as a postdoc in the Laboratory for Information and Decision Systems at MIT. In fact, that's where we actually first met. We both had a lot more hair and a lot less gray hair too. And then he joined.
And we were smarter then.
What's that?
We were smarter then, I think.
And he then joined the HP labs, where also, as many of you know, that very, very well renowned labs in California. After that, he joined the electrical engineering department at University of Minnesota, where he held the McKnight University Professor and Vincentin Hermes Liu Chair in Electrical Engineering. Right now, at Minnesota, and currently he's a professor at Duke University. As I just said, he just joined last fall. I could go on actually for the whole talk, basically talking about these accomplishments, but I'm not going to do that because we want to hear about what he has to say. His interests are in computer vision, both theory and applications, computer graphics, medical imaging, and machine learning. I think he's doing a lot more machine learning these days. He's extremely well published, over 300 papers in these areas. He has a book, in fact, one of the earliest books that I know of in nonlinear diffusion with PDEs from Cambridge Press in 2001, and many, many, many more things. And so I'll cut it off at that and let him take over. Thank you for coming. It's a pleasure to have you.
Thank you. And thanks a lot for coming. And I hope that this will be just the beginning. I met Hamid a couple of times, and I've been in the area since July, but moving is harder than you can ever think. So it's taking me time to do these more visits, but hopefully this will be just the beginning. And what I decided to talk, there's different activities in my group, but I decided to talk about these two topics which are connected, which is how we find representatives in data and how we do network inference with topological constraints. And we're going to see in a second how they are connected, actually, when I get to the second topic. There's almost this very similar math. So the first part is about computing data representatives. I'm going to define the problem. And this was work done with Ehsan. Ehsan was a PhD student at Johns Hopkins with René Vidal, and now he's a postdoc with Shankar Sastry at Berkeley. So, you know, everything comes to a circle because you have a distinguished new faculty from Shankar's group. So everything is just, it's a very connected graph, as we're going to see. And we have a couple of publications, and we were trying to get another for now, but he moved, so things slow down a bit. So the basic motivation is that you give me a lot of data, and there's a lot, people are very excited today with big data. The big problem, one of the big problems with big data is there's a lot of data, but that doesn't mean there is a lot of information, and people confuse the two. And mostly there is no information in data. If you actually take probably a proportion of what information there is in Facebook compared to the data that there is in Facebook, it's probably very small. Okay? And you have to try to find it. And that's one of the challenges. So we're just trying to come with one formulation to find what's actually good information in data. So it's a subset, we call them representatives of the data. And that might be very useful, for example, in video to summarize the video. And it can be also, so this is an example that I hope you can see better in the screen. The red frames are frames. So this is from the debate, from the previous debate between current President Obama and what many wish was the current president, Hillary Clinton. And this was a debate, and the red is just basically some keyframes that basically, as I'm going to define in a second, every other frame is just nothing else but these frames in some way or another. And so you can summarize, and then you can also improve computational time. If you want to do nearest neighborhood, if you just have representatives, you just have to compare to them and not compare to all the data. So it's a good way to simplify. That's the goal of the first part of the talk. It's just to understand what's actually I need to extract from the data, and everything else is just really data but not information. Also, not least important, as I'm going to show you, once you understand what are representatives of data, you understand what are outliers in data. And sometimes you want to remove them. Sometimes actually that's important information, the outliers. So outliers are things that representatives don't represent them. Okay, it's a very simple definition once I put everything in math. Okay, and we're going to see that we can get outliers very easily from this. So that's basically the definition. We want to, you give me a lot of data. In a second, I'm going to show what we call representatives. But the basic idea is I'm going to give you a few data points that everybody else is nothing else but just different views at those same data points. There is a lot of work in the literature, and we could spend weeks and weeks. And this is related, for example, with k-means or quantization. You just have a lot of data, and you're trying to define a vector that represents data. So a lot of work. And all of the basic work in this area has, some of it is excellent, but most of it has one fundamental problem, is they define the problem as a non-convex optimization problem. And then you're not very sure what you're getting. So vector quantization is one example. K-means examples of great algorithms, but they're non-convex problems. And we're going to try to do it convex. So the contributions is we are going to basically define formally representatives as data points that everybody else is a linear combination of them, more or less, close to a linear combination. So for those that are already anticipating, we're going to try to find subspaces in the data. Okay? So you're very powerful. We too are very powerful if you guys are just a linear combination of us. Okay? That's going to be the definition as I'm going to formalize. We're not going to make big assumptions, only that we have more data than representatives. Makes sense. Okay? We are not making any assumption about the dimensionality of the data. We don't care about it. We don't make, that means some of the theory will care about it, but not the formulation. We don't make any assumptions about how many representatives. We don't make assumptions that the data lies all on a low dimensional manifold, nothing like that. Just giving more points than representatives. And that's a reasonable assumption. It's going to be convex. The problem we're going to formulate is convex. And as I say, it's going to basically, there's going to be some theory that will explain how we are detecting these representatives, and it's related to low-rank models. And I'm going to explain you the geometry that comes out of it. And we're going to be able to do this online, because big data, you cannot deal with a lot of data at the same time. So I'm going to show how we deal with that online. No algorithm today that deals, so if you have big data, and you know, some of the people were explaining to me distributed. So distributed is important not only because you have distributed sensors, because it's the only way to deal with big data. So if you want to, this is something that I think it took a while the community to understand. When we have, and I was having this conversation 15 years ago with one of the top machine learning people, and he couldn't understand what I was saying at that time, and hopefully he understands now. You know, we use in MATLAB 100 by 100 matrices. And then when you used to say to people, yeah, but I need to invert a 10,000 by 10,000 matrix, then the response, yeah, if it's sparse, that's OK. Yeah, what when I need to invert a 10 million by 10 million matrix? Open your sparse theory matrix inversion, and you're going to say that breakdown. OK? And Rafi Kaufman a while ago said there is no math yet for big data, because the data is so huge that you can, things that are natural for us. Algebra 1, we learn how to invert a matrix. You can't invert a matrix. If your algorithm has a matrix inversion, forget about it. Okay? You can't do that today when you have a lot of data. So it's important to be able to do it online. And these are some of the characteristics. Before I go into that, let me just, because this is inspired by something I've been working a lot in recent years, is sparse modeling. And I want to just explain that and explain how we get inspired by sparse modeling but get away from sparse modeling in certain sense. So in sparse modeling, you have data points, this y1 to yn, and you normally have a dictionary. You can think about a pre-specified dictionary like Fourier, DCT, wavelets. And you're going to try to represent your data as a linear combination of elements of your dictionary. Okay? So normally, what you formulate is the following problem. You basically have a fitting term that says every data point has to be a linear combination of elements of my dictionary. You don't want many of them to be active, so you want to put here an L0 norm that counts how many columns of D you're actually using, but you put an L1 norm because the L0 norm is NP complete to optimize for. So this is your penalty. You have to have good fitting and not use many. Okay? You run over all your data points, and what you're going to try to do in sparse modeling and dictionary learning, if you're just trying to encode, you forget about the dictionary, you just try to encode. If you're trying to learn the dictionary, you're learning both the code and the dictionary at the same time. So this is standard in sparse modeling today. It's kind of the most classical thing. There are very good algorithms out there. The two most popular are KSVD by Mickey Ladd and MOD. They're just variations one of the other. So you basically end up learning a dictionary that in such a way that your data can be basically represented in that dictionary. And by the way, with Alex Bronstein and one of my postdocs, Pablo, we know how to do this in real time on mobile devices today. You can do this online. There's good stuff to do this. Okay? Now, what's the problem with this problem? This is just a normalization, by the way, nothing serious. The problem here, this is a non-convex problem. So this is a biconvex problem. If you fix D, the problem is convex. If you fix the code, X, the problem is convex on D. It's not convex on both of them at the same time. Okay? Then you don't know exactly what's happening there. Okay? There is only very few papers that show convergence of these to a global minima in certain cases. And you know, we have used it a lot, and I have nothing against local minima. But it's a problem with non-convex problems. So this is a non-convex problem. So once again, you have a fitting term and a regularization term, in this case, sparsity. Just standard regularization fitting problems. So we want to start from this but get a bit away from it. And then we define what we call sparse modeling representative selection. And the basic idea is that the dictionary is going to be the data. Okay? So once again, look at this. I should have written, in a second, it's going to be in matrix form. But if you look at this in matrix form, it says y equal dx. Okay? So now D is my data. I'm not going to let you find D. I'm going to let you find D as a subset of your data. So this is going to be the problem. I'm going to write Y. Every element here is a linear combination of everybody else. Trivial solution, diagonal. You're okay? But I'm going to make something smart. I'm going to say you're a linear combination of everybody else, but everybody should be sharing the else. So I'm going to, this is D, but I'm not going to be using a lot. I'm going to try that everybody uses only a few. Not only that you use only a few, everybody uses the same few. And that means that I'm going to ask for the rows of my coefficients matrix to be as many of them 0 as possible. So the row here, C1, tells me if I'm using Y1. Okay? So I'm going to penalize, not for the L1, but I'm going to penalize for what's called, for example, the L12, which is the number of non-zero rows. You're going to pay a price. Once you have a row that is non-zero, do with it whatever you want. But I'm going to make you pay for every row that is non-zero. And that basically you can either pay by an indicator function, your zero, non-zero, or you can pay by an L1Q, which becomes convex problem. Okay? So once again, the basic idea here is I'm not going to let you put wavelets here because I want you to learn the dictionary. I'm not going to let you learn the dictionary because it's not convex. I'm going to say, hopefully, there is enough data that you have seen that the data itself is a dictionary. Okay?
So this is your assumption of the model?
That's my model. Yeah, that's my assumption. My assumption is, and this is, my assumption is you have seen enough. So the assumption here mathematically says that all your data lives in the union of subspaces created by the data itself. Every data point is a linear combination of a few others. Not one subspace, multiple. But the data, you have seen enough. That
this has been verified through empirical data.
Yeah, I'm going to show that. Yeah, it's actually quite surprising. But let's just input a couple of things. So we are used to representatives. That's how America works, isn't it? I mean, we select people. This is very important. We don't select a linear combination of people. We select people. And we hope that these senators that we elected combined, they represent me. So the dictionary, this is, what?
And it's only a hope.
It's only a hope. That's why there is an equivalent there. It's not equality. So it's not, and this is going to be very kind of gross, but it's not that we take the arm of one person. So it's not that, okay, we go to elections and we say, okay, I like your head, I like your arms, and I like your body, and I'm going to create a dictionary. We don't do that. We say, I like you, 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 and together you represent me. So I'm selecting a subset of the data to represent me. I'm not allowed to invent data. In a few places you can write in candidates. Write in will mean learning the dictionary, but nobody, whoever wrote in, I don't know anybody that writes in. Seriously, you know, people put my mother or things like that. But normally, you're given a list, and you have to pick from that list. Okay? That's how election works. And I just gave this talk in Israel, so I have to use people from the political in Israel, which is important people. I'm going to tell you something else. And this is my view of science. So you ask for empirical data. Every paper out there today is a linear combination of other papers. So think carefully about that. Okay? Hamid is thinking.
As long as it's not a degenerate.
No, all what you need is that one of your papers is a representative. Then we are happy. You're in trouble if you are not selected as a representative. I took information theory with Tom Cover at Stanford. And he said, when I took the class, he said that you can redo all information theory based on only 3 papers. This is kind of sad, but he said 3 papers. We could go and burn all the information theory papers, and we're going to redo all of it based on 3. And he misquoted one of them, according to what you explained today in the morning, but he said reason and complexity, Shannon, of course, and Lempel-Ziv. Everything else is derivatives of that. Not linear combinations, but not farther away from that. I went back after the class to my information theory friends at HP. I was at HP at that time, and I said, he's absolutely correct. There's a 4th paper that he wrote that is new, but he wouldn't say that. He said everything else is a combination of the past. So this is science today, and there's nothing wrong with that. Okay, so it might sound silly, but it's nothing wrong that we take the literature, particularly if we're engineers, we take the literature and we solve a new problem with tools that we are given. Okay? So that's the premise. The premise is that the data basically is nothing else than a linear combination of itself, and then we formulate the problem. We say data has to be a linear combination of itself. The trivial solution is diagonal, so we're going to penalize we penalize for a 1Q norm. Normally it's a 1-2 norm or a 1 infinity, which means I'm going to penalize for every row of your coefficient matrix that is non-zero, because you're selecting a new representative. So that will be like having a country with 3 million senators. We can't. And that's only 7 million. But that's, yeah, actually there's 7 million, so it's 8 million representatives. But it's like a department. But normally you have to pick a subset of them. Okay? The last term is just a normalization that makes all this translation invariant. Forget about that. It's a technicality. Okay? So that's the problem. This problem is convex. Okay? I have this problem, as long as you put here q greater than 1, is convex. Because I'm not optimizing for y. I'm kind of indirectly optimizing for y. But I'm not allowed to change the columns of y. I'm only allowed to select from y. That's the whole problem. So I'm going to tell you a couple of results about this. One is a technical result. The two technical results, I'm going to show you some examples. Assume C is positive. So once again, there was no assumptions in what I made before, but I'm going to make assumptions just for the theorems. There was an underlying assumption that my data lives in this. By the way, there was not even an underlying assumption that your data lives on anything. If your data lives on a ball, then it's not subspace, then the C matrix won't be sparse. Sorry. I won't have many 0 rows. It would just happen. It won't be very good, but there was no assumption here. There is a hope here that your data lives in low-dimensional subspaces, and then the matrix C will be very sparse. But if not, so be it. And you're going to end up at the end and say, oh, I input 1,000,000 points, and my representatives are 1,000,000 points. That means that this data is just random around the high-dimensional space, but that normally doesn't happen. For the theorems, we make some assumptions, for example, that C is positive. So what happened is that I'm going to just basically describe in words. What we are saying, when the dimensions fit, the representatives are the vertices in the convex hull. So if everything is in one subspace, I didn't know that. I threw you data that lives in one subspace. I throw that to the previous optimization problem, I get the convex hull as representatives, if C is positive. It's a cute result. You might say, oh, I don't need this to compute the convex hull. Actually, this is more efficient to compute the convex hull in high dimensions than any other technique that I am aware of, because this can be done very efficiently today. So it's a convex hull. Just a cute result. If that helps us later on, not very clear. But it's a convex hull. Makes sense if C is positive. What happens if I have multiple spaces? If you have multiple independent spaces, the representatives are the convex hull of each one of the subspaces. So you plug that optimization problem, and you get the convex hull of each one of the subspaces. Okay? So it's just a result. And we have a couple of other results. But this kind of to give us a bit of the geometry of what we're finding. How do we deal with outliers before I show you examples? An outlier will only be useful to represent itself, and nobody else will help you to represent the outlier. So this is the structure that you expect of your matrix C when you have outliers, or maybe even here. So this is my matrix C for real data, a lot of non-zero rows. But all these guys, we order them on purpose. Just don't help anybody, and they are not helped by anybody. So how do you detect outliers? Any way that you want to measure energy in a row. The energy is 0. That point is not important. Nobody wants it. The energy has only one non-zero or a couple of non-zeros, the row, that means you're an outlier. You were selected as a representative because you need to represent yourself. Then you're an outlier. Okay? So it's a very simple concept. If a lot of people want you, you're not an outlier. If nobody likes you, you're an outlier. And outliers are good to remove, or sometimes they're good to detect. And we have, so you can invent whatever metric you want there. We just describe one, and we show that this is very powerful in detecting outliers. But you know, the graph shows it, but I'm going to show it with examples. How do we do online? So this optimization problem I told you is convex, but it's very computationally expensive. How do we do online? Very simple. You basically have seen data, and new data shows up. So you will have a matrix that has all data and new data, and you will have to solve the optimization problem. But then you become smart and say, hey, but haven't you just told me that my all data can only be represented by just these 7 data points? You just told me that. So okay, then throw your all data, just keep the representatives. Okay? So now you give me 100 million points. I'm going to take 1,000 points, find representatives, throw 1,000 points, keep the 2 representatives, give me another 1,000. Now I have 1,002. I find representatives. Maybe they like the ones you find before. Maybe those will be eliminated. And then you slowly solve the problem. And at the end, you find the representatives of all the data. Yeah?
What if the things which you throw at the beginning were representatives for what's going to come later?
No, careful. I will only throw it if there is something here that can represent these guys. There is an issue here that if the data change a lot, you might consider with a connector, you might consider these guys as outliers. So if you're doing online, you have to be careful with the previous one, because you have to remember, yeah, you're only being used for yourself, but you've been used for 1 million in the past, so I'm not going to throw you away, because there's a lot of people that are coming with you. Okay? So you have to be careful combining both. But otherwise, if this new data, nobody can represent these guys will show up in the matrix. And then you remember, when you're doing the filtering of outliers, you say, no, I'm not allowing to throw these guys. I'm allowing to throw outliers here, but not these guys. Or you can have memory and say, this is a dynamical system. Oh, these guys were from the very beginning of the data. I'm throwing them because it looks like the system has changed.
Conversely, though, do you need to go to the end? Because it could be that perhaps you've seen as much data that's informative as you have seen. In other words, do you have a criterion that tells you that?
No, we haven't. It's an interesting question. We might say, hey, your outliers are not, your representatives are not changing. Stop doing this. Right. Yeah, we could put a criteria. We haven't done. It's a good point. It's a very good point. Yeah.
And there's a possibility that, for example, you divide the data into 100 pieces. And for each of them, actually, is representing the same piece of data in this 100. But for each part of this data is outlier. So it's possible for you to get rid of it.
Yeah, all this has breaking points. Yeah. We have to be careful. When we do online and outliers, they just have to be a bit careful. Yeah, I agree. I think there was, yes.
You'd be doing the process like start with 100 data, 100 points here and 100 points there. They do their thing, and then combine them.
Yeah, we are doing that. Yeah, it's kind of another version of online. Yeah.
For the representative, have you record how many original data you can represent?
Very good. Very good point. I'm going to go back to that point in a second. Yeah. So this is just an example I showed before. It's a video, and you can look in details. The representatives make sense. So it's where big scene changes are happening. This is just another scene in tennis, and there will be the PDFs will be available. But you look at them and say, it makes sense. It's just representatives of digits if you want to do basically classification. This is what you ask. We find representatives, and then we mix them. So now I have 2 very small sets of representatives, and I say, hey, give me a subset. And this one was basically almost repeated, so it was dropped. So you can start playing all the games, that means and depending a lot on the application. And now I'm going to your question. I can actually start looking at the energy of the rows and say, wow, you're really popular. So I can order my representatives. as well. I could remember that when I'm doing online. That's certainly a very valid point. I could do a weighted L12 to say, hey, these guys are important, try not to throw them. I could do that. We haven't done, but it's still convex. If you give me the weights, it's still convex. If you ask me to find the weights, no. But if you give me the weights, it's a convex problem. And this is the case where we order the representatives according to the energy in the rows. So this is a database of faces. And basically, it's the same person from multiple views and multiple lights. And you see, this is the most important one. This is the second most. Third, wow, it's the light from different directions. So you order the representatives. And now if you're in a budget, computational budget, you can say, hey, sorry, I know you wanted 5, but I only have space for 2. You keep the top 2. So you use the same tricks to detect outliers that to keep how important you are. And we use this, and I always put tables, but I don't like to dwell on them. We use this for a classification problem, and you get very good results. To say, hey, instead of doing nearest neighborhood to everybody, just do nearest neighborhood to your classifier, to your representatives, and you're expected to get good results. Then we recently extended this to, hey, what happens if I don't give you the points? I give you pairwise distances between them. The geodesic, diffusion, whatever. I give you some correlation, something say, this guy and this guy are very similar. Then you can do the same formulation that it's almost the same, but now your data is not X, your data are these pairwise distances. Okay? So you don't have to have the data, and then you solve a convex problem. We have some nice properties as well. We prove some theory. But the main reason I want to show this is because I really like the result of this. So we wrote this paper, everything but one paragraph. And we look for the sentences that are representative of the paper. Okay? We took every sentence. We did the standard thing that people do in text analysis. We took every sentence, and we create an histogram of words for that sentence. So that's my vector. And we created distances between the vectors, and we plug that. And we say, which sentences represent the whole paper? Now remember, this is a paper about finding representatives from pairwise distances. And these are the 4 top sentences. Given pairwise dissimilarities between data points, we consider the problem of finding a subset of data points called representatives or exemplars that can efficiently describe the data collection. Done. I just defined the paper. That was find the most important sentence in the paper automatically. Meaning everybody else, a lot of other sentences use the same words than in this sentence.
But
not in the order.
Yeah, that's what.
Because it's an histogram. Not in the order.
That's what.
Uses the same words.
Okay.
Yeah. So you see, we know each other for a long time.
That's what I was going to ask.
Yeah, it's a distribution. Yeah, it's 0 order. It will be interesting to do first order.
You're scary. You're reading my questions now.
It will be scary if I read your answers. But it's very cool. This is almost like an automatic abstract writing. And if you read the others, it has some of the key theoretical results in the paper. Yes?
What metric did you use for this?
We just took basically the distribution and L2 between the histograms. Yeah, so it's very nonsense, although it's one of the most popular using for this type. But going back to Hamid, maybe in the distance we should have taken order between the words and things like that. But just by doing that, we got an automatically generated abstract, more or less.
That's very good.
It was a cool example. I was surprised when SN did this. But I think it's very important. I also think it's very important. Yeah, I also agree with that. Yeah. The third sentence is about one of the theorems. So, okay, so let me conclude this part. Large data sets do not mean large information, and we know that. And data is very redundant, and this is what we're exploiting here. Okay, so come on, a video is 30 frames a second. How much can we change? How fast can we move? And we did a convex approach. either from the data or from pairwise dissimilarities. And we explain, when we take the points, I explained the convex hull. I didn't tell you the theory, but for the similarities, we showed that we get representatives in the clusters. So when you're talking about the similarities, there is the classical notion of clustering them according to similarities. This computes data points in each cluster. Okay? And as I said, we can do online and other things. So let me just tell you the second part, and then we can go for more questions, because it's almost the same math, and it's going to be very short. And this is work with a grad student that I have, Marcelo Fiori and Pablo Musset, and we just had it at NIPS. And Marcelo is, so here is the formulation, and you will see it's almost identical. So you have a p-dimensional vector. So this is standard graph inference problems or covariance estimation. You have a p-dimensional vector that we assume in this case that, although there's new results that show that this doesn't have to be exactly this, is a Gaussian distribution from zero mean and sigma covariance. And then you formulate the following problem. You're trying to build the graph with as few edges as possible. So this is trying to build a graph. Say basically a node is linearly dependent. So be careful, this is in p dimensions. So basically the coordinate 1 is linearly dependent on coordinates 7 and 9. And I want to have the least possible dependencies. And there is some theoretical result, so this is an L1. It's not an L12. It's the whole matrix B should be very sparse, should be symmetric, and diagonal 0. If you have diagonal non-zero, then it's very sparse. I'm not penalizing for rows. I'm penalizing for total sparsity. And then you don't find anything. If you solve this problem under certain conditions, the matrix B is the inverse of the covariance sigma. Okay, and this is standard. It's not our result. It's a standard, and there's a lot of beautiful theory about this, including now theory where this is binary vectors or categorical data. Okay, so this is standard. People plug that in and do graph estimation based on this. What we wanted to do with Marcelo is a bit more. Just, if we are talking about politics, this is an example. You plug in your data points, votes from senators. This is the inference of the graph. This is one of the classical examples. Blue are actually Democrats, red are Republicans, and you see that they are modulo a couple of outliers. They basically, their votes are party line completely. Okay, so from their votes, you infer the graph. What we wanted to do with Marcelo was add constraints. One of the things that happen very often is that you are going to infer these graphs, and you get a graph at the end that has no, it's not what you expected to get if you know the physics of the problem. Okay, and I learned today that we can add other constraints that we haven't looked at that, but one of the constraints is what happens if somebody comes and tells you what's called the eigenvector centrality, which is the principal eigenvector of this connectivity matrix P. Somebody comes and whispers in your ear, I don't care about the graph, but I know this is the structure. Why that principal eigenvector is important, I assume that many of you know about graph theory even more than me. This, I always joke, is the richest eigenvector ever created because it's behind Google PageRank. So this is $1 billion above eigenvector. Okay? This eigenvector, why so important? Because when you get x equal xb, and then you iterate, you get b to the n, and the only thing that survives is this guy. Okay? So if the internet is, if Facebook has a lot of people, the more people have, the more this guy is important because everybody else dies. Because the eigenvalues are below 1. So to the end, they die. So Facebook, Google, the larger the net, the more this eigenvector is important. And this is the PageRank. So what happens if you have a PageRank, an eigenvector from Facebook, and you want to put it into Twitter? So it turns out that you can do the same type of game that we had before. And now you gave me an eigenvector. You gave me the principal, so I'm going to design B to maximize this. This is a minimization, so I put minus. This is the definition of eigenvector. So the first eigenvector is the one that when you multiply by the matrix gives you the maximal linear product. So I put that in here. So I try to find a B that recreates the eigenvector you just told me. Before Hamid asked me, I need to know the order. If you didn't give me the order, invite me in a month and I tell you how to do it. We now know how to do it, or we're working on how to do it. If you give me, oh, I know it's this, the order, I know these are the nodes. One, I don't know which one, but this is very important. This is the second, but I don't tell you which one. I don't tell you the order. So it's like you give me Facebook and Twitter, but you mix the users. You didn't label the users. Then I need to add a permutation matrix here. And then the problem is non-convex. This problem is convex still. So you do that, and that's one idea. It's convex. This is just a toy example. This is on the left is the original. You basically create Gaussian distributions. You create a covariance matrix based on that. If you do the ordinary estimation, you get in the middle, has no resemblance. And if you say, hey, I know the eigenvector, you get the one on the right. You can do this kind of online. Let me just skip this. We took stock market data, because you might say, how do I learn the eigenvector? So one way of learning the eigenvector is use other data. So you get data from the stock market, and you say, hey, work very hard on half of the data, learn the eigenvector, and then impose it to the second half. And you impose it as a variational formulation. It doesn't have to be equal. And when we do that, we actually show, because we know we have grand truth, we actually show that we basically significantly reduce the error, just sometimes by an order of magnitude, the error in your graph estimation. So that's one thing that we did. The other thing that we did was, and this is what I mentioned before, motifs. There are things that happen in graphs, and one of them was mentioned in your presentation today, is these triangles. So triangles happen. We are friends, you're friends. So there is triangles. And so how do you impose triangles? So basically, when you create a connectivity matrix B, if you do B square, so basically every entry ij in B square is the number of paths between ij that have 2 steps. You do B to the n is n steps. So I square B, and I try to basically motivate for a lot of 2-step paths, which means a lot of triangles. Okay? So I put that in here. I'm looking for a B that has this n comes from the B itself. So this is non-convex now. My weights on B are I motivate a lot of 2-steps paths. I want a lot of them. And that will create triangles. Okay? If you want a lot of 4-step paths, just put B to the 4th. Okay? So it's just another example. And this is just, again, we start from a graph that we know. The middle is the graph that you create if you don't do, and the one on the right with a lot of reds actually recreates triangles. So, and these are important. The funny part here is people were happy with this. You give this graph, which is basically gene network. You give this graph to a guy in biology, immediately looks at it and says, this is not a real graph of a real biological system. We'll tell you immediately.
That's what I was going to ask you in terms of when you say this is good, what is the metric?
Okay, we have validation data that people don't know, but that's the real metric. But if you look at the people that have been doing like gene networks, they tell you they have to be.
If they have this,
they have that. They look at this and they say, well, there's not enough triangles here. I don't know what's enough, but there's not enough here. Yeah. Actually, they have studied the distribution of triangles in those. Yeah, but it's more like that. But in this case, we have real data, so we can validate. But what constraint to add has to be told to us somehow. So basically, we impose that as an example. So the idea here is that we are basically adding constraints to the graph inference problem. And we have many others. I just picked two. But I'm going to tell you, for example, the other. That say, hey, Facebook and Facebook and Twitter should have the same, I don't know which one, but they should have the same centrality. So I jointly inference the network for both of them with that constraint. Or you can come and tell me, I don't know what, but they should have the same number of triangles. Because whoever's are friends in Facebook, they should be friends among themselves in Twitter. So I don't know how many, but please have them have more or less the same. So this is what allows you to do that. And this is what allows you to get away with, nobody told you how many triangles, but they tell you there have to be some consistency among the. So that's why I was asking today to you on lunch, they have to have the same homology. You can come and say, yeah, you know what? The word, so these are basically, I'm just inventing a type of application that you could think about. So you have nodes about countries, and you're trying to define where there is a hole in supply of food. And you have a lot of data about rice, and a lot of data about, I don't know, meat. And you say, you know, where there is a hole, there is a hole. There is no rice and no chicken. So infer a graph that gives me the same location of the holes. That makes a lot of sense to do. Okay? Instead of just infer it, and then you say, hey, there is a. Now, if you have sufficient data, you don't need this. But when you have scarce data, noisy data, this basically helps stabilize the system to say, hey, these guys have to be coherent.
When you add that constraint, the path constraint you were talking about, so how does your, you said, of course, the convexity goes out the window. So how does your...
We do coordinate descent. You compute B, you compute the M, you plug the M, you compute the B again. And don't ask me any theoretical result about that. Okay. We have no idea.
Okay.
Yeah, we weren't happy with that, but yeah, there might be other ways of doing it. But,
yeah.
I think that was my, that was my last slide.
Let's thank our speaker. Any questions?
Yeah, I have one.
Yes, please.
For this application, I can see it's very interesting. But could you comment on this application on a network that is changing all the time?
Yeah.
Because then your signature, it might be effective for T1, and then for T2, those representatives may change. So how would you maintain consistency?
Start again.
Can you repeat the question?
The question is, what happens when the network is changing in a dynamic fashion that maybe representatives now are not good in the future? And I don't know that. I don't know the answer to that question. So you can have, when you put normal online, so everything we do in science has assumptions. So in online algorithms, there is an underlying assumption that things change slowly. And then you put a forgetting factor. You say, hey, your new data has to remember a bit, but not too much. That's how it's done online. Or what I'm saying is you can do it here. What's that forgetting factor? I have no idea. The problem has to dictate it. It's the same as any online problem. You know, if you keep your old data, 3 years later might be completely irrelevant. I agree. And normally you just put forgetting a decaying forgetting factor, something like that. Yeah.
Is there sort of a criteria that you will know that to which point you need to change your representative?
You could do what I think he asked. Say, hey, don't do online. Every time do a new chunk of data. And start comparing representatives with representatives. If you find that they're completely different, say, hey, forget the past. Things have changed a lot. If you find that basically there's a new one, and then one of the previous ones becomes an outlier, just drop it, and you start. So you could try to create criteria for saying, hey, this data is changing, or this data is the same. Look, you get a new set of representatives. All of them can be represented by the old set of representatives. Nothing has changed.
Thank you.
So you could, but I'm not saying that there is a bulletproof solution to this. You know, the application will dictate. Yeah. I mean, if you look at papers, you know, we were discussing about that. You know, look at papers. You know, what I was doing at the end. Big data. There will be two words that will become representatives, and they weren't representatives 10 years ago. I mean, science is an example where the representatives completely change, but gradually. It's not that the people in Nano woke up one day and said, we're going to do big data from now on. They just had one student doing big data, and then two, and then three. And then you look at them and say, hey, weren't you doing Nano 20 years ago? Yeah, that's old-fashioned. Then if you put a decaying factor, it will be old-fashioned in the representatives as well.
Is there, for instance, your first, the first application you looked at in terms of the video sequence? Is there any way to basically the whole idea is that what's really important is actually occupies a very small.
Yeah, that's the whole point.
The rest is all background. Forget it. You don't need it, right? Is there? Have you thought about perhaps then using more like of a predictive model in a sense where now that I've gotten my ground, quote unquote, ground truth.
I could start thinking about Kalman filtering.
Yeah, that kind of stuff. Right.
Yeah,
that kind of stuff.
It's an option. We haven't done that, but it's certainly an option. Yeah.
Thinking,
Which, by the way, why do we assume linearity? That would be kind of my first thing. Why? Okay, these are representatives, but maybe you increase the power by 2. So what? Maybe this should be square. So it starts asking a lot of questions about this x minus xb. Maybe I should make better models. Yeah, certainly. We have representatives in nature. I was making the joke about senators. It's not a linear combination. There are others, and that opens a very interesting question about believing in representatives, but letting them be a bit more powerful by doing other things. Yeah.
So the data which you consider here come in vector form, right?
Yeah.
So I think we can extend some, if you have a set of graphs, to pick representative graphs.
Yeah, certainly. You can do tensors. You could
go in this form, let's say.
As long as you give me as long as you give me a fitting term that doesn't break my convexity, this will be convex. But it will be application. So once again, take just a bird's view and think about the concept. And then for the particular data and particular application, we might need to change the formulation completely.
Your input should be the distance between the graphs?
Maybe, yeah. The distance stays convex problem. Yeah.
This should be a metric though. Cannot be any similarity.
To do any theory, yes. You can do whatever you want for the formulation. But hopefully it will be a metric.
Shao?
Yeah, so I was wondering, is there some way to handle in shifted features? For example, if we have an input data, it's just the shifted version from the previous one.
Yeah, so our formulation is a fine invariant.
But if we just consider the linear combinations, then it is possible that it cannot linear combine, it cannot represent.
Very good. So don't give me the data, give me features.
I see. So
don't give me the Fourier magnitude of the data. If you know that that's a problem, in the distance, in the metric, put it. Make sure that the distance between a shifted version of the other is 0. Yeah. Okay? So I'm not saying I know how to do that for everything that you want to get rid of, but that's part of your job, to give me a distance matrix that took care of all the nuisance.
I guess it's maybe important for image processing, since the features can change the position.
Yeah, but I could do shift features in image processing. They are shift invariant and rotation invariant.
I see.
I don't have to put the frame.
I see. Thanks.
Yeah, that will be kind of more natural to do.
Any other question? Well, if not, let's thank our speaker again.
And again, it's just I'm on the other side of the road. So I wasn't going to make a joke, but since we're being broadcast, we have to be careful.